All right, so welcome to chemistry, but we're going to start off talking about measurements. So significant digits, these things right here, these are they're numbers based on real measurements. Let me make this a little bit smaller. Okay, so the reason why significant digits are important is because we want our measurements to be accurate, right? So the degree of inaccuracy increases as our digits get larger. All right, so let me give you an example. So an estimated digit, so significant digits, we'll say so significant digits are all real measurements, right? Plus one estimated digit. So if I looked at this triple balance here, right? So let me get my pen back. All right, so all real measurements. So the top one here is on 0. This one here is on 20. And this one here is 6 point, we'll count over 1, 2, 3, 4, 6.4. So that represents the real digits of a measurement. So right now I have 26.4. But if you look at the end here, if I make it just a little bit bigger for you, right, I'll move over here. So if you look at it here, right, so it's not really on the 0.4, right, but the real numbers it's passed is 26.4, but then we have to estimate. So we estimate how far between the next two numbers it is. So you can say 24.4, all right, and this is your estimated digit. Right? If you said 24.5 or 24.6, it doesn't matter because that's our estimated digit, and then we'll give a unit grams, right? Because we have to give a unit to it. All right. So let's start the. If you use an electronic balance, we won't be back in class right now. They take care of it for you. All right. So if I was to look at this one, let's take a look at this. So when you estimate, so if I take this to real measurements, right? So there's a couple things here. The lowest scale increment, right? So this is a, first of all, this is a graduated beaker. And those graduations right here, so graduations are lines of measure. So I have my lines of measure. So my smallest scale increment here, so you could say that my smallest scale increment I go 40, 50 is 10 milliliters, because each line here represents 10 milliliters. Because this is 60, so this would be 70, then 80, 90, 100. Okay. So my real measurements here, so if I took this right here, so my real measurement would be 100, 110. And then I would have to estimate how far. If it's halfway between a 10, it would be 5 would be my estimated. Maybe 6. So if I make estimated 5, my 5 would be my estimated. So I could say, I could represent this as 115 milliliters. So the estimation makes it more accurate. All right. So those are the significant digits are. So let's figure out how to work with numbers. Because oftentimes we've been taught how to manipulate numbers, but not taught what numbers are. So numbers refer to real measurements. Right, so rules having to do with zeros. Right, so it all starts with this. So our first rule, right, trailing zeros are never significant. Right, so they just hold a place. Right, so 13,000 here. Right, so 13,000. These numbers here are not considered significant. So we could say that this has 2 significant digits. The trailing zeros just tell you where the measurement is measured from, right? So number 13,000 is not very accurate, or it could be very accurate, but not very precise. All right, now I'll talk about that a little more. All right, so leading zeros are never significant. So these zeros here are not significant. Again, this has 2 significant digits. Oops. This just tells you start counting in the thousandth place. Right? Rule 3, right? Trailing zeros after decimal are always significant. Right? So these would be the significant digits here. Right? These leading zeros just tell you where to start counting from. Right? So this one you would say would have 5 significant digits. Right? And the last 4 zeros found between are always. So these count. So everything counts because these zeros are between real numbers, so they count. So this would have 6 significant digits. Right, so now we know the rules for numbers. Let's figure out how to do math. Right, because if I told you, if I gave you a math problem, I said 100 plus 5 equals 100, right? Right, because this one, the 100, the only significant digit here is that 1. It's in the hundreds place. Now, the 5 has 1 digit, and that's in the ones place. So we have to talk about accuracy and precision. So accuracy is getting close to the intended result, and precision is number of digits in reference to a decimal point, right? So this first number is accurate to the hundreds place. It lacks precision. The 5 is accurate to the ones place. So the 5 is more precise than the 100. It has too much precision. So my answer can only be as accurate as a less precise number. Okay? All right, so I can only give my answer to the precision of the least precise number. All right, so measurement. Oops, we're doing multiplication. I thought I was doing addition first, so we'll come back to that. So anyway, that's kind of where we go. So here's the rule for, so the measurement of the smallest amount of significant digits determines the digit of the answer. All right, so let me rephrase that for you. All right, so the answer can only have the number of significant digits as the operand, or the number in the problem with the least number of digits. So if we go back here and look at this, if I look at this 0.3287, this has 4 digits because the 0 doesn't count. Right? 45.2 has 3 digits. So my answer can only have 3 digits. Right? So if you plug them into your calculator, you'll get 14.85724 grams, which is too many digits. It should be grams squared because it's grams times grams. Right? So I'd have to round it right to 3 digits. So this 5 rounds up and makes the 8 9, so I would have 14.9, right, grams squared, right, and it's rounded to 3 digits because my answer can only have 3 digits. Right, so that's our multiplication rule. Make sure you write down your rules because you're going to need them. All right, significant digits, calculate addition, subtraction. So total cannot be more accurate or more precise than the least accurate measurement. Okay. So right? All right, so this one is precise, has precision to the tenths. This one has precision to the hundredths. And this one has precision to the tenths. So my answer can only be the tenths, because the tenths is least precise. Right? It has precisions like reference to the decimal point. Right? So determine the precision of your answer. Right, so if I add these up on my calculator, this is what I get. And that is too precise. So again, I'm going to round to the tenth, so my 8 will round up. I'll get 180.3 kilograms. Right? Right, so this is precise to the tenths. So if I have mixed operations, then I'll follow the rules of math. So I'll do parentheses first. Right, so if I have this, right, this is a division problem. Division is number of digits. So this has 6 digits. This has 4 digits. So when I do this division problem, I get 4 digits. Right, and then subtraction is to the precision. This is precision to the tens. This is precise to the thousandths. So tens. Right, so I have to do my answer to the tens. So when I multiply this across, I get this number, way too precise. So I'll go ahead and round this one up to the tens place. Then I get my answer. Right, so just follow the same rules. Now you'll have a sheet to do today, and I'll give you the answer to some of them so you can check your work as you go, and I'll talk about it at the following Zoom. Scientific notation, the only thing remember about scientific notation is you keep the significant digits. So scientific notation is how we make big numbers smaller, more manageable to use. Right, so if I have the number of atoms in a mole, right, 6.02 times 10 to the 23rd is called Avogadro's number. We'll talk about that later. Right, but if I had this number and I had to put it into scientific notation, these 3 numbers are significant. Right, so if I had this number here, I would have to display my number with 3 significant digits. Right? So remember, if I'm taking zeros out, my exponent becomes larger. If I'm putting zeros in, it becomes smaller. So I'll have to make this large number smaller so my exponent gets bigger. Right? If I count at 3, 6, 9, 12, 15, 18, 21, and then I'm 21, 22, 23 to get to the 6. So scientific notation is always one real number followed decimal, right? That's scientific notation. All right. So you should be able to get that. So if you look at this bottom example, right, I'm having to make 0.00501. Remember, it has 3 digits because the leading zeros don't count. But this one, I'm making the 0.00501 larger, because I'll make it 5.01, right? So since I'm making it larger, my exponent gets smaller. So 1, 2, 3. So you should all know that by now. Had enough math. Right, percent error. I'll just introduce this. This is in your homework sheet, but we usually do this a lot in chemistry and biology, and it's the way that we show how accurate we are. So percent error calculations are used to compare test results to a known accepted quantity. So the percent error, make sure you write down this formula somewhere, but I'll continue to remind you on it. It's the measured value, right? So this is another thing for measured, you could say, is this is your experimental. Right? An accepted value is your, maybe your expected. Right? Your experimental minus your expected is another way to look at it. Right? Divided by your expected. Right? And that'll give you your percent error. Right? So if the accepted mass of an object is 5 grams, right, and you measure on your digital scale 5.02, right? So again, this is your right, but I expected, right, 5 grams, I get 0.004 or 0.4%, right? That's just percent error. Okay, so that's a quick and dirty explanation of significant digits. You can do your work, and I will talk to you soon.